Alright, today we are going to be looking at section 6.2, real applications of normal distributions. Now we talked about normal distributions in the standard form before, and these are going to very easily transfer over. So for the most part we'll explain how they transfer, do a couple of problems, and then continue onward. Alright, so what we're going to have is that either our mean is not 0, or standard deviation is not 1, or possibly both. And what we can do is we can standardize that distribution, that normal distribution. The way we do that is by calculating what the z-score would be for a particular value of x. That means that we will use z is equal to mu. Z equals x minus mu divided by sigma, and this will give us our z-score. So that will take our standard deviation from a certain sigma over here to 1. It'll take our mean from mu to 0. And the same shaded region will give us the exact same area. Once we have what our z-score is, we can use technology or a 2 chart to determine what our probability would be. Alright, let's look at this example. What proportion of men are taller than 72 inches? Height requirements for shower heads. Which, by the way, makes no sense. You can raise a shower head, lower a shower head. If you're shorter than 72 inches, can you not take a shower? I'm not sure why they're saying this, but I don't know. Let's just go with it. Alright. Now, the mean for the height of men is 68.6 inches, with a standard deviation of 2.8 inches. And we want to find the percentage of men taller than 72. So we want to find the percentage of men such that x is greater than 72. Alright, so let's take a look at how we would do that. Well, x is greater than 72. Assume they are normally distributed. We have our formula here. What would our z-score for that be? Well, we are looking for the probability that x is less than 72, and that is going to give us a z-score of 72. My apologies. X greater than 72. So we're looking for a z-score that will be 72 minus our mean, which is 68.6, and divide that by 2.8. And that will give us, just plug that into a calculator. We can plug it into Z, but I'm going to go ahead and put it in my calculator. It will be 72 minus 68.6 divided by 2.8. That'll give me 12. 2.8, not 0.28. 1.21. Alright, so now I simply look up my z-score for 1.21, and my probability will be 1 minus that z-score, because I want greater than 72. So I'm not looking for a left area, I'm looking for a right area. So z is equal to 1.21. So we go here, and again, by symmetry, we could say negative 1.21, which would give us 0.1131, or that 11.31% are below or are above 72 inches. But let's take a look at the positive value. So 1.21 gives us 0.8869, and we subtract that from 100. That will give us 0.1131, exactly what we had. Alright, so they're doing 1 of 6, so we've already done it, so we are way ahead of them. But let's go ahead and continue on taking a look at their example, 0.1123. Alright, so there we go there. And we can get that, and this is showing how they did it. Z is x, 72 minus mu, 68.6 divided by 2.8 gives 1.21. That is the z-score that we looked at. Looked up the z-score in A2 and subtracted that from 1, and that gave us our 0.1123. Now, some z-score tables will also let us choose to the right or to the left for the z-score. Right, and this is just showing us how to do the subtraction. Interpretation, about 11%, the design would be unsuitable. Now, let's take a look using Excel. Now, we still have Excel, and we can either use the z-score like they did before and use the normal z-distribution, or we can use this normal distribution. Notice that this one does not actually have the S here. That means it's not standard. So we can put in a mean and a standard deviation. So I'll go ahead and try to use this one. The probability that x is greater than 72 inches is going to equal the probability, it's going to equal 1 minus the probability that x is less than 72 inches, which is equal to, and I'm going to go ahead and put equals, equal, I'm using this here, do not mean to write it like that, norm, distribution, so x, 72, I want everything up to 72. Mean is, well, our mean is 68.6 inches, our standard deviation is 2.8 inches, and remember this will always be true, but I don't actually want that normal distribution, I want 1 minus that normal distribution. So 1 minus that distribution, up to 72 inches, will give me 0.11231939. So we get extra digits from that. And that is 1 minus the normal distribution. And here we have to put the number we're looking at, everything up to that, what the mean is, what the standard deviation is, and again, the true. It will always be true for us. So they're showing how graphs can be useful for finding that. Which is great. Don't confuse z-scores and areas, of course. Z-scores can be negative, areas cannot. Areas always have to be positive and between 0 and 1. Right. So how to find the values from known probabilities. So what if I want my probability to be up to a certain amount? Well, I can basically do the opposite of what I did before. So first we find the z-score corresponding to the probability that we want. Say if we want 95% of all men to be able to fit under the shower head rather than just 89%, which is what we got before. Then we need to find the z-score corresponding to that. We could use the A2 chart, which 0.95 would be, well, between 1.64 and 1.65, or we could use technology to get it. Now, for technology, I would use the inverse, give me the probability, mean, and the standard deviation. Or I could just do the z-score like that. Either way. But let's say I just want to do the, no, I want 95% of the people here. So I would use this right here, x, such that the probability that I'm below it is 95%. So that would be equal to the probability, or equal to norm, the inverse of the probability, which is 0.95. The mean is, again, 68.6, and my standard deviation is 2.8. So I would need to have my shower head 73.2 inches above the ground if I wanted 95% of men to be able to use that. Now what if I wanted 99% of men to be able to use it? So we got 72, that went up to 73. Now it's 75. And notice I could even make this ridiculous. So 99.99, so that's 1% of 1% of all men, and that would be 80 inches. And let's say I wanted, we got a billion, 1 in a billion, so 1,000, million, billion. 85 inches if I wanted 1 in a billion men not to be able to use it. Meaning we got about 5 or 6 men in the entire world who can't use it. So it would be 85 inches. And if I wanted to make it 99% chance that they wouldn't be able to use it, put a couple of more 9s here. Now we got 88. So if we had something that was 90 inches off the top of the ground, almost all men would be able to use it. Unfortunately, that would be really high above most people. So that's why we don't have them that high, usually. Okay, that was a bit of a tangent, but let's go back here. Alright, now go back to that. There we go. Now, let's say we do find the z-score instead, rather than using the direct inverse like I did. The direct inverse is very nice. You will not be able to use the direct inverse on an exam, though, unless you figure out how to do it on your calculator. Now, should you figure out how to do it on your calculator? I would say yes. It could be useful. But if you can't, then we can do it with just the z-scores as well. So the way you do that is you figure out what your z-score would need to be based on your probabilities, and then you would calculate what that x would need to be based upon that z-score. And you use this formula right here. X is equal to mu plus z sigma. And that's just a different form of the conversion form. Okay, so previously we had looked at an example where only 46% of women were able to satisfy the height requirement for U.S. Air Force pilots. What would be the maximum acceptable height of a woman if the requirement would allow the shortest 95% of women to be pilots? That is the 95th percentile height of women. Now notice that this says the shortest 95%, so there's no lower limit on the height of a woman, but there is an upper limit. So let's figure out what the z-score would be for that. So we would have a probability of 0.95. So x would equal our mean, which our mean here we can see is 63.7 inches, plus our z-score. Now a z-score associated with 0.95, well, we can look that up. So we want 0.95, definitely going to be over here, 0.95, so it's going to be down here. No, not definitely going to be here, but let's see, 0.95. Oh, but you know, it is there. So 1.65, maybe 1.64. I'll go ahead and go with 1.64. Now notice 1.64 and 1.65 are equally distant from 0.95. So we can choose either one. I'll go ahead and pick 1.64. You can pick 1.65 if you want. On a test, I'm not going to count out because of the small difference. So that will be our z-score. Now going back, multiply that by our sigma, which is 2.9, and that will give us our height. Now we want women to be 68.5 inches or less. 1.645. Oh, they go in the middle. Aren't they special? Alright, so there are two different ways you can do that. Getting the exact same solution. Now we get that. We get 68.47. Just using that. Or, like they did, we can also use technology. Excel. X mean standard deviation. We can just use this. So for women, 95% height, that would be is equal to normal inverse. We want a probability of 0.95. We got a mean of 63.7 and a standard deviation of 2.9. So 68.47 inches. And that's what we get in Excel. That's what you get with your calculator. It's looking for the what height 95% of women would be below. And that is 68.5%. Okay. So that seems reasonable. That is if we want a maximum height. Do we want a minimum height? No, because it doesn't matter. Oh wait, there should be a minimum height so you can reach the controls. Or you could just make smaller airplanes. Either one of these would work. Alright, a little bit shorter, and that is section 6.2. We shall be back soon with section 6.3.